Hello and welcome back. In example 4, we have a trapezoid that's sitting in the water. Part of it is submerged in the water, part of it's out of the water. So in figure 2, we have the bottom of the trapezoid is 4 meters, the top of the trapezoid is 6 meters, those are the two parallel sides. And then 2 meters of the trapezoid is below the water, and 1 meter is above the water. Let's figure out the hydrostatic force that's acting on this surface or this plate. Now, one thing to note is that the only force that's acting on the plate is the part of the plate that's underwater, right? The top of the plate, there's no hydrostatic force that's acting on that. There isn't any water up there. So it's only when you go below the water that suddenly now you have a force due to the water acting on that plate. So that's something to note when we come up with our limits of integration. Let's take this trapezoid and put it on a coordinate system. There are different ways of doing this, but I like to use the symmetry of the trapezoid to help out. So I'm going to go out 3 in each direction because the trapezoid extends 6 meters. I lost this. Okay, let me draw this again. Yeah, it's the first time this happened. So we have -1, -2, and -3. And we're going to go up 3 because from the bottom to the top is a distance of 3. Looks like we're in meters, which is nice. And here's our trapezoid. Going from 2, 0 to 3, 3 for one of the sides, -2, 0 to 2, 0 for another side, and then -2, 0 to -3, 3 for another side, and then all the way across on the top. Now again, the water is only here at y equals 2 in this picture. That's the water. And we're going to analyze what happens when you look at just a horizontal strip of that trapezoid. So at a given y value, this is y sub I. We're going to look at the strip right there. There. Kind of got squeezed. The strip got squeezed a little bit. All right, the thickness of that is delta y. And again, our goal is to find the pressure that's acting on that strip. We're going to find the area of that strip, multiply them together to get the force that's acting on that strip, and then add up the forces of all the other strips. So we're getting a formula for this force acting on each strip. Okay. Go down just a little bit and find the pressure acting on that strip. Well, our formula is rho GD, where rho here is, because we're in the metric unit system, rho is 1,000 kilograms per cubic meter, and G is 9.8 meters per second squared. D here, the depth of the strip, we'll get by looking at the distance from the strip to the top of the water. So that's going to be the y value of the top of the water, which is 2, minus the y value of the strip, which is y sub I. So you can kind of tell that for the depth, it's always going to be the y value of the top of the water minus y sub I. Not too bad to find the depth. So then this can simplify to 9,800 times 2 minus y sub I. The units here, just to talk about the units, are going to be the units of newtons. per square meter. So newtons per square meter. You can get that because 1,000 is in kilograms per cubic meter. If you take the kilograms times the 9.8 meters per second squared, kilograms times meters per second squared is newtons. And then you have this extra 2 minus y sub I meters, which cancels with one of the units of meters on the bottom to give you only 2 units of meters on the bottom. Now we can get the area. Whoops. Now we can change the color, then get the area. Now to get the area of the strip, well, it depends on where the strip is. When we are at the bottom of the trapezoid, then the area is smaller. At the top of the trapezoid, the area is bigger. Of course, we never make it to the top because we're only considering strips that are underneath the water, right? Well, we're going to want to get a formula for this curve, the side of the trapezoid, the right side of the trapezoid. And that's a line, and we can get the equation for the line by thinking about a point on the line and the slope of the line, both of which we can get. We can choose any point on the line here. We can choose 2, 0 or 3, 3. I'm just going to choose 2, 0 because it has 0 in it. And then the slope of the line is given by rise over run. If you think about the rise over run from 2, 0 to 3, 3, the rise is positive 3 in the y direction over positive 1 in the x direction, which is a slope of 3. So using point slope form, we have y minus 0 equals 3 times x minus 2. There's the point 2, 0, and then the slope 3 that we found. So we have, solving that for x, we get x equals y plus 6 over 3. There you'd have to, either one way of doing it is distribute the 3 to the x and the negative 2, add the 6, and then divide by 3. We want the x values because we're interested in figuring out that horizontal distance. Now the other line ends up being x equals negative y minus 6 over 3. Negative y minus 6 over 3. Kind of makes sense because they have opposite x values, right? If you have a positive 2.5 on the right, it's negative 2.5 on the left. So it's just the negative of whatever x values we have on the right. So then if you want to find the horizontal distance, you can write the right x value, which is y plus 6 minus 3, minus the left x value, which is negative y minus 6 over 3. You could actually just look at that and say by symmetry, it's just twice whatever the right x value is. And that's a faster way of getting there. What I'm doing is just writing generally. You can always think about it as a right minus left. But definitely if you can find shortcuts like just multiply by 2, that can work really well. So because of that 2 that you're going to get, you can actually pull out the 2 and the 1/3 that's in both of these fractions, and you'll end up with a y sub I plus 6. I forgot to write y sub i's for these. Delta y. And this is in cubic meters. The sun is setting. You can kind of tell on the back wall the sun is setting, and that's why my face is suddenly bright. Oh, there we go. Just had to move forward a little bit. It's adjusting. Okay. This is not a good habit to get into for making these videos. This is not in cubic meters, this is in square meters. That's what I get for not paying attention. Okay, to get the force acting on that little strip, we're going to take the pressure times the area. And when we multiply those together, you'll get 9,800 times 2/3 ends up giving you 19,600 over 3 times 2 minus y sub I times y sub I plus 6 times delta y. Then what we can do is write that the force is approximately equal to the sum of all the little forces. I'm going to go right into it. Oops. This is 19,600 over 3 times 2 minus y sub I times y sub I plus 6 delta y. That's the Riemann sum part. And then the integral is going to get you the exact force on that trapezoid. Now here we're integrating across the underwater part of our plate. So that's going to be y equals 0 to y equals 2. To y equals 2. That's the only part of our trapezoid that's underwater. So integral from 0 to 2 of 19,600 over 3 times 2 minus y times y plus 6 dy. All the y sub i's turn to y's, all the delta y's turn to dy's. There's only one delta y. This one you can distribute the 2 minus y and the y plus 6, and you'll be able to integrate term by term. So I'm going to put a dot dot dot. You eventually get 784,000 over 9, which ends up being approximately equal to 87,111 units of force. Here are newtons. Okay, I better stop this video before it gets totally dark. Thanks for watching, and see you in the next video where we're going to look at center of mass. Thank you.